Most problems of science, engineering, or economics involve change of one variable with respect to others. We model such problems using differential equations. The differential equations could be ordinary or partial. In general, we cannot solve these differential equations analytically unless we take serious simplifying assumptions. Technique that we will learn now, how to solve numerically differential equations. In particular, we will talk about the ordinary differential equations and initial value problems now. In initial value problem, we seek the solution of certain differential equation at x greater than x naught, where the value of y, the unknown, at x equal to x naught is given. The difference between analytical and numerical solution is that numerical solution does not give us a continuous y. Instead, it will give us y only at selected discrete location that we denote with this subscript I. To solve differential equations, the first step is we start from the differential equation and then we create something we call difference equation through discretization of the derivatives. And then we solve these difference equations. Sometimes we use the techniques of linear algebra that we have learned before. So let us see that how we use Euler method, which is the simplest method of solving initial value problem. Let us see how we use that now. An ordinary differential equation in general, an nth order equation, is a function of x, y, and then the derivatives of y up to dny dxn to be 0. Here, when we solve ordinary differential equations, we have to keep in mind that this variable x, which is the independent variable, is known, and we are interested to find y at certain given locations of x, which we are denoting by x subscript I. So let us say the simplest case will be, of course, this n equal to 1, and that will give us a differential equation of this form. Y prime, that is dy dx, is a function of x and y for x greater than x naught, where y as x equal to x naught is given as y naught, which is our initial condition. Here this x you can think of as a time, or sometimes we call this the time-like variable. So we know the present, which is x equals x naught, and we want to predict the future by solving the differential equation y prime equal f. This sort of equation, which is known as this first order, that is n equals 1, so it is first order, and this is an initial value problem. The first order initial value problem, if we learn how to solve it, we should be able to solve higher order initial value problems as well, and we'll talk about it later. But let us first focus on how to solve first order initial value problem y prime equals f of x, y. The first method, or the simplest method that we learn, is the Euler method. In Euler method, what we do, we start from this differential equations y prime equal f of x and y, and then we apply the finite difference discretization to create the appropriate difference equation from the differential equation. So when we apply finite difference here, we know that my y prime is dy dx, which will be given by yi plus 1 minus yi divided by h plus order of h. This is the truncation error of the order of h. And here we know that h is xi plus 1 minus xi. This is something we call step size or grid size. Of course, we know that from this equation y prime equals x, f of x and y, I can write y prime, that is yi plus 1 minus yi by h equals f of xi yi. Now I can multiply h both sides, and I can write, taking yi to the right hand side, I can write yi plus 1 equals yi plus h into f at xi yi. This sort of evaluation of x at I point is known as explicit. That means we are evaluating f with known x and y. So please note that in this difference equation, yi plus 1 equals yi plus hf xi yi. Only yi plus 1 is unknown. Yi, xi, these are the past values, or you can say these are the current value, and yi plus 1 is the future value. So the present values are known, and the future value yi plus 1 we are calculating. So we can start at I equal to 0, that is the initial condition, and then I take for I plus 1, I can calculate knowing the initial condition, and this is how we can proceed. So essentially, this function f of xi yi, I have several options how we can evaluate. I can evaluate it at xi yi, I can evaluate it at xi plus 1 yi plus 1 as well. But I chose to evaluate it at xi yi just to make my life easier. Because if I evaluate it in xi yi, then you can see that in this difference equation only the left hand side yi plus 1 is the unknown, the right hand side is completely known. If I evaluate f at xi plus 1 yi plus 1, then f is unknown, and we have to solve an equation to find yi plus 1. In the current form, which is the explicit scheme, in explicit scheme I am evaluating f at xi yi, and thus the entire right hand side is known, only the left hand side yi plus 1 I have to calculate. In this scheme you can see that our discretization here is forward difference, which has a truncation error of the order of h, and then it is multiplied by h. So truncation error in the difference equation comes h square, and that would be of course the local truncation error. If I now keep on marching in at I, then the global truncation error will be additions of many of this local truncation error, and it will go toward the order of h. So the overall scheme will be only first order accurate. So truncation error will more or less scale with the grid size here, that is the h. These are the type of scheme we call first order accurate scheme. Okay, so how to implement the Euler method then in reality? Here you see a small pseudocode of Euler method. We start with the knowledge of f of xy, and then x0 and y0 are our initial condition. H is the step size, which we can take here as a constant step size, and n is how far I want to go. So I start from I equals 0 initial condition, and then I calculate yi plus 1 at yi plus h multiplied by f of xi yi. Since I know the nature of this function, knowing xi and yi, I should be able to calculate f of xi yi. I keep on calculating this. I update this xi with xi plus h, and I keep on running this loop until I reach my desired value of n. The problem of this approach is illustrated here. You can see that if this blue line is my analytical solution, then this black line will be my numerical solution. And usually in Euler method, the difference between the analytical solution and numerical solution tends to grow. So it's very important if we use Euler method to keep this difference within acceptable limit. And how do you do that? Of course, we know that this difference will be in some way related to the truncation error. So what we can do to begin with, that we should keep the h to be sufficiently small so that this error, as much as the n will go, the error up to this yn should be within our acceptable limit. The other approaches are, of course, something more complicated. One way we can do is that we can use implicit Euler method. This is usually much more accurate. In implicit Euler method, this f we evaluate at xi plus 1, yi plus 1. So my overall difference equation will look like this: yi plus 1 minus yi by h equals f at xi plus 1, yi plus 1. Therefore, now I have the equation yi plus 1 minus hf xi plus 1, yi plus 1 equals yi. So you can see that now, unlike the explicit scheme here, in the implicit scheme, I have to solve an equation involving yi plus 1 to get the yi plus 1. In explicit scheme, it is simply a calculation. The right hand side is completely known. Here I have to solve this equation to get yi plus 1. Of course, this will be more complicated. This fundamental difference of explicit and implicit scheme we'll discuss more carefully later on. You can now try an exercise. Here we solve for y given the differential equation y prime minus twice x cube plus 12x square minus 20x plus 8.5 with an initial condition of y equal to 1 at x equal to 0 and a step size of 0.5. The numerical solution, we can use the Euler method. The analytical solution is also not difficult. After we do the numerical and analytical solution, we can plot the results. This will be your first exercise. I'll suggest you carefully go through this first exercise, compare your analytical and numerical results before we get into more complicated procedures for solution of initial value problems. Thank you, and that's all for this lecture. I'll see you in next class.